Good morning, everyone. Hello. Can you all hear me? Hello. I think you all are ready. Ready to start number theory. This episode we are going to do application of principle of mathematical induction in divisibility. Why suddenly this topic? Because we are doing divisibility, and divisibility by Euclid's lemma we have done mainly. Euclid's algorithm we have used for divisibility purpose. Now the concept is that we have to find divisibility by another way, and the principle I am going to discuss with you, that is called principle of mathematical induction. But before that, let us do few sums on divisibility which you can always do by using your common sense. Last class I told you a little bit about this kind of divisibility. It means if a number divides another number, then the second number can be expressed as a multiple of the first one. We have taken two numbers this manner, like b and a. Then if b is completely divisible by a, then we can state that b equal to m into a, isn't it? Just a minute. So if number b is there, we can write b equal to m into a when b is completely divisible by a. A, b, m all are integers. And I have also mentioned that if two numbers x and y are divisible by another number z, integers, then we write mathematically this form: z divides x and z divides y. This implies z divides a linear combination of x and y, that is ax plus by. This is very important, and this is a common sense expected from all of you that you can apply in solving sums. Like when z divides x, z divides y, then z will divide a linear combination. Combination means that you are multiplying x by some integer a and b also integer. They may be positive or negative. A and b both may be positive, both may be negative, one positive, one negative, but they are integer. So z will divide ax plus by. You can see the reverse way also. Like when you are saying that z, whether it will divide ax plus by or not, you can prove it separately that z will divide ax, z will divide by, then z will divide their sum, their difference, even their product. Am I correct? Like when you are saying that 7 divides 21 and 7 divides 14, this implies that 7 divides 21 plus 2 into 14. This is always true. And this is also true that 7 will divide 3 into 21 minus 2 into 14. Why? Because there is 3 into 21 means 63, 63 minus 28, 35, 7 will divide 35. This way you can check. I am going to show you some problem which can be done without using any theorem, any lemma, just by using your common sense and remembering the meaning of divisibility. So let us start with the first one, where you have to prove that the number 3 divides 4a plus 7 if 3 divides a plus 1. A is integer. Even I have not mentioned here, remember a is an integer. Okay. So if a is the integer, it is dividing a plus 1, you are going to prove that it will divide 4a plus 7. How to prove this? We are going to answer this manner, that 4a plus 7 we will write like 4 into a plus 1 plus 3. A is integer, a plus 1 also integer, and you know that a plus 3 divides a plus 1. So this is like ax plus by. What is a over there? A is 4, x is a plus 1. That 4a plus 7 is divisible by a plus is divisible by 3, because this part divisible by 3. This part I have cleared in the last session. In the product, if one or both of them divisible by 3, then the product will be divisible by 3. So this part already it is given over there, that 3 divides a plus 1. So 4 into a plus 1 is divisible by 3, and 3 always divisible by 3. Okay. So what about their sum? Their sum going to be divisible by 3. Here you all understand? Immediate application of divisibility concept, and you don't need any lemma or theorem for this. It's just common sense. If 3 divides a plus 1, you can take any integer. Like suppose you have taken a equal to 5. Then 3 divides 5 plus 1, 6. 3 divides 20 plus 7, 27. Clear? So for any integer, it is true. Those who are attending the class today, I will request you to go through the previous videos, previous sessions I have shared with you. Link is already shared with you. You can go through once for better understanding. But today's class, you don't need any concept from the previous classes. But when I'm going to start the next class, definitely you need the concept you gain from episode 1 and episode 2. Okay. So let us proceed. Let us see what other kind of sums may be there which you can solve with the help of your common sense. Okay. No concept of number theory. Number theory is there already involved. It is required definitely. But it is based on common sense. Any student above class 8 can use this method. Let us do this one. Show that if the positive integer a divides 7n plus 4 as well as 42n plus 37, then A is going to be 1 or A is going to be 13. I told you sum is based on your common sense only. You just think little bit, then it is solved. Before I start solving, you solve it and get ready with your pen and paper. Do it with me. Okay? Learn it with me. I'm also a learner, no? So let us solve this one. Show that if the positive integer a divides 7n plus 4, it means wherever you get 7n plus 4, you can state that it is divisible by a. To prove that 42 plus n plus 37 divisible by a, we need to express 42n plus 37 as multiple of this. Let's see what happens. So we write 42 plus n as multiple of 42n plus 37 as multiple of 7n plus 4. You write 6 multiplied by 7n plus 4, but not completely divisible by 7n plus 4. Something is extra. 37 is there and it is 24. You write plus 13 over there. Now, this part is divisible by what? Positive integer a divides 7n plus 4. So a divides this one. Because 7n plus 4 is divisible. 6 may not be divisible, but 7n plus 4 we know. So this is divisible by a. Now to make this thing 42n plus 37 divisible by a, we have to make this second part must be divisible by a, and this is enough to get the value of a. This 13 must be divisible by a. My question for you, what are the divisors of 13? 13 is a prime number. Little bit idea you all have. Past video I have explained. I did not do anything new. Just I told you that 13, it's a prime number. It is divisible by itself and by 1. Okay. So if a divides 13, then a must be what? A must be divisor of 13. So a must be equal to 1 or 13, because 13 is a prime number. It is divisible by 1 or 13. So a must be equal to 1 or 13. Here, hope all of you have understood. From here we are getting the value of a. It will be either a or 13. Let us go for next one. Find all integers n such that n divides n square plus 1. See, these are all integers. Integer, all of you know. I am telling you today's class. Today we will be doing all kinds of integer. Maybe positive, negative, maybe 0 also considered. Number theory is your natural numbers. First, I'd like to tell you, I'd like to remind you. For today's class, when we are discussing divisibility, a common topic in IOQM exam, they don't consider always integers which are greater than 0. Question may arise where integers are negative. 0 also maybe. Okay. So at least today's class we should take care of those parts. So all integers n means to find all positive, negative, all. Okay. Now when you are going to find integer n such that n divides this, it is clear that it is obvious that n divide n square. This is true. N always divide. This symbol we have used for divides. A divides B. This statement in number 3 implies A divides B. Okay. So here n always will divide n square. 2 will divide 2 square. Minus 2 also will divide minus 2 square. 5 divide 5 square. Like that. N will be dividing n square always. Now the dividend has two parts. When you are going to prove that this thing divisible by n, then this part quite obvious, divisible by n. This part has to be 1 has to be divisible by n, means n must divide 1. So what are the integers possible so that n divides 1? This implies that n equal to plus 1 or minus 1, because they asked you to calculate all integers. All integer means it can be positive or negative. So n is equal to plus minus 1. Clear? Next one, find all positive integers in such that n plus 1 divides n square plus 2. N is any integer. You can check it with n equal to 1. If n equal to 1, this is not possible. See, 2 never divides 1 square plus 2, 3. For n equal to 1, what's happening there? For n equal to 1, n plus 1 is 2. N square plus 2 is 3. 2 does not divide 3. Okay? So for n equal to 1, it is not possible. But we are not going to prove it with that manner. I mean, if I start this manner, for n equal to 1 will prove, then n equal to 2 will prove, then we'll prove it for general value of n. No, not now. We'll start just after finishing this. This you can solve with the common concept that if n plus 1 divides this thing, it will divide all parts of it. So you should express n square plus 2 in the form of n plus 1 first. You write this thing as n into n plus 1, but not adjusted. Here it is n square plus 2, you got n square plus n. So subtract n, add 2. It is adjusted. So this thing is n into n plus 1. Obviously, it is divisible by n plus 1, nothing to do over there. Let's see what happened in the next part. It is n plus 2 minus n plus 2. I write minus of n plus 1, then plus 3. I hope you have understood. This little manipulation, all of you understand. Now you have to find positive integer n such that n plus 1 divides n square plus 2. N square plus 2 now has 3 parts. What are the parts? N into n plus 1, one part. Only n plus 1, another part. 3 is the last one. Clear? So this part, n into n plus 1, it is divisible by n plus 1. This thing, divisible by n plus 1. Then for divisibility, if n plus 1 divide that whole thing, n square plus 2, this part must be divisible by n plus 1. So for divisibility, n plus 1 must divide 3. Okay? 3 is a prime number. Its factors are what? 1 and 3 only. So only 2 possibilities are there. So for n equal to 0, it is possible. Because 0 plus 1 is 1. 1 will divide 3. And it is true for n equal to 2 also. Okay. So these two values will make it sure that the whole expression, if n is equal to 0 or n equal to 2, the whole expression n square plus 2 divisible by n plus 1. But they have asked you find all positive integers in over there. Okay. So to find all positive integers in, we need to neglect n equal to 0. So the only solution is n is equal to 2. Clear? You all understand? This is the only solution, n is equal to 2. Let us go for next one. Find all integers in such that n plus 2 will divide n cube plus 12. You just think for 1 minute, then I'll tell you. You all have passed class 8 level, you know factorization. Try to use factorization. Do from my side. I mean, n cube plus 12, you should express as the factor of n plus 2. May not be fully, but partially you can do it. Part of it will be divisible by n plus 2. You understand what I am going to say? So, to find n, first we take a term separated from here. N cube plus 12, we are writing in the form n cube plus 8 plus 4. This is nothing but n cube plus 2 cube plus 4. This is n plus 2, n square minus 2n plus 4 plus 4. Isn't it? You all understand? This manipulation is okay with you or not? I have used a very common method over there, that to prove it is divisible by n plus 2, I am separating this. N cube plus 2 cube always divisible by n. Okay? So when you are writing n cube plus 12, it has become n plus 2 into n square minus 2n plus 4. So this part you don't have to think. This is always divisible by n plus 2, because n plus 2 is a factor over there. Now for divisibility of whole of n cube plus 12, this part must be divisible by n plus 2. That n plus 2 must divide 4. What are the values of n you suggest? This implies that n must be 0, or you go by trial and error method, because 4 is a very small number. If you take n equal to 0, okay. N equal to minus 1, all integers they said. You have to take n equal to minus 1 plus 2. Done. Then you take n equal to minus 2. No, minus 2 means 0. 0 does not divide anyone. Okay. So take n equal to minus 3. For n equal to minus 3 plus 2 is what? Minus 1. Minus 1 divides 4. Then is there any negative value? You take n equal to minus 6. Minus 6 plus 2 is 4. 4 divides 4. Similarly, you take n equal to positive value 2. 2 plus 2, 4. Any other positive value possible? No, because it will be more than 4. It cannot divide 4. Isn't it? So these are the integers I got here when this n plus 2 will divide what? This n plus 2 will divide n cube plus 12. Let us go for next one. Next one going to be very challenging for you. I'll wait for your answer. You can write in the comment box. Exhibit three integers that are relatively prime but not relatively prime in pairs. What are those integers? Can you tell me? You can write here. Exhibit three integers that are relatively prime but not relatively prime in pairs. I mean, suppose three numbers you got A, B and C. A, B and C, they don't have a common factor. But there may be a common factor of A and B. There may be a common factor of B and C. No hi-fi concept is required. Just ordinary idea regarding these integers. What are those integers? You go by trial and error method. That also will work nicely here. I am helping you. Take two integers 6 and 10. What do you observe there? They are not co-prime. There is a common factor, isn't it? There's a common factor between them. What's the common factor over there? That common factor will be equal to, the common factor will be equal to 2, isn't it? The common factor will be equal to 2. Now, if common factor is 2, then take another number where there is a factor with 6 and 10 both. 6, 10 and 15. So we are taking 15. In my mind it was playing at 15. 6 and 10 there is a common factor 2. 10 and 15 there is a common factor 5. 6 and 15 there is a common factor 3. 16 and 15 they are prime. They are prime. They are relatively prime. I mean, all three integers you don't get a common factor. So the kind of sum I have discussed here, this you can say that IOQM type. But only IOQM type? No. These concepts are very useful for JEE also. Okay. First few classes meant for those who are appearing for JEE also. Okay. Next year or next to next. These concepts you need. When I am doing Chinese remainder theorem here, then you don't need. That you don't need. I'll mention that is exclusively for Olympiads. Some topics are there exclusively for Olympiads. Those who are aiming, they need to know it. I'll explain. Whatever. Today's class, the first part will be this that I told you, isn't it? The process diagram I made here, that divisibility part is just over. Not really, it is not over. Divisibility has no end. You will find divisibility next day, next to next day. But the way you need to get the common idea of divisibility that I have explained by using Euclid's lemma, Euclid's algorithm little bit, and just your common sense. Okay? Let us start this part now. Principle of mathematical induction and then a few applications of it. Stay with me till the end of this session, then you will get the real benefit, and hope all of you are doing it with me, learning it with me. Okay? When I tell you something, I learn, myself learn. Okay? I'll explain how I am also learning from you. But you need to practice with me, because otherwise you'll forget. After 2 days only, you'll not remember anything. Okay, let us start. Principle of mathematical induction. Just let me tell you in brief, this boy is climbing the stair to go as high as possible. What is the basic criteria? Initially, he was standing on the base. Okay? Then he has to step on any one of the stairs. He cannot step on the 10th one, but he can step here in the first stair or second one or third one. More than that, so he will not be able to climb up only. No. So normally we start with n equal to 1. But it may be 2 also. You are in a hurry. You will start climbing very fast. So as first only you have stepped into the third stair. That will be risky also. But suppose you have done. Okay. N equal to 1, 2, 3 all are possible. But wherever you are stepping into, that is going to be your initial step. Then you can go for next one, next one, next one. But if I can state that you are on a particular rung and then you can move to the next rung, next step, then I can say that you can climb as high as you want. Because when I am saying arbitrary, it may be anywhere on the stair. When you are situated in any one of the steps, and for that I can see that you are able to go to the next step, then I can assume that you can climb as high as you want. So you are showing confidence over there in the diagram, isn't it? So you can climb as high as possible there. Now let us see another one, that is domino effect. Dominoes are placed in a row. If you knock over the first domino and ensure that each domino next knocks over the next, then all dominoes will eventually fall. First domino pushing the second one, second to third one, third to fourth one, finally they all will fall. We have seen that when bricks are arranged in a row, someone just striking at one end, then all will fall gradually. Okay? In mathematics, how does it come? In mathematics, you can draw a conclusion. You can't draw a conclusion just by seeing that first one is given, just given a hammer, or you have just pushed it towards the second. It will not ensue. Mathematically, whenever you are going to prove, you have to be 100% sure. Purity in mathematics, purity in science, judged by mathematics. This subject is there lagging behind all subjects to prove the purity statement. Okay? So, if we see that in this process, an arbitrary, say kth one, just pushing the k plus 1 at one, kth one falling, k plus 1 also falling, then we can say that it can hit the last one also and last one will fall. This is mathematics. Okay, just by seeing that I have pushed it, it may be there is some block over there that is rigid over there. Okay, or due to some other reason it is not ready to be inclined, not ready to fall. But that will not happen. That I told you in the beginning, that if kth one falls, k plus 1th one falls, I did not mention which one is k and which one k plus 1. It may be 49th and 50th. It may be 51st and 52th. It may be 101 and 102th. These are arbitrary. It means I mentioned the condition over there. If kth one falls, k plus 1th one also will fall. Then all will fall eventually. Okay? This is mathematical induction. Let me make it clear with you that how this concept helps to prove something in mathematics. This is inductive method. When I have the scope, I'll discuss the deductive method also with you. Deductive method you are already using. Inductive method we will be doing too. Comparison will be done later. So here is a formal statement I have written for you. Let Pn be a statement that is defined over every natural number n. Prove that Pn is true for all natural number n. We must establish two steps. What are the steps? Base step. Base step is what? You must hit the first one. You must reach the first one. Okay? This is basis step or base step. Initial step. That in case of that climbing the stair, the boy may be initially at n equal to 3. Can happen. Okay? That's why I've taken that as n0. N0 is the initial value of n. Okay? For that, for this problem, if you are doing it for n equal to 1, then n0 going to be equal to 1. But that I told you in staircase, people may be situated at n equal to 2. I mean step 2 in the beginning or step 3 in the beginning. In that case, you should introduce the concept of n0 equal to 2 or n0 equal to 3. N0 stands for the starting value. Okay? Starting value 1 in most of the cases. Normally, we take n equal to 1. Inductive step, what you are going to prove? That I have mentioned already. I am seeing that kth one falling and it tells k plus 1th one to fall. Then I draw the conclusion that all the dominoes will fall eventually. Here, when the boy is climbing with confidence, if he can move kth one, for that k plus 1th, it means this is inductive. If nth one he has done, n plus 1th also done, we will assume that it is done. He can go as high as possible. Okay, so in number theory, if you are able to prove that in principle of induction, mathematical induction, you are able to prove that for n equal to k, n equal to k plus 1 also valid. That is statement pk valid, pk plus 1 also valid, assuming that pk is valid. First we'll assume, see the statement here. There is an assumption required. You assume that pk is true for some arbitrary natural number k, then pk plus 1 also true. You prove it with the help of pk, then you can say that it is true for all natural numbers. Okay? Let me take one simplest example, and this you learn it with me, those who have not done it before. Okay, taking the first problem for you, there is to prove 1 plus 2 plus 3 up to n equal to n into n plus 1 by 2. Those who are studying classes 11 and 12, some class 10 student also must have proved this one, but today's class will do it with the help of mathematical induction. See how to do it with the help of mathematical induction. Okay, does induction really help? Let us see. Answer. So what will be the basis step here? I mean, for n equal to 1, the base step, initial step, for n equal to 1, LHS is equal to 1, because one term only to be taken into consideration, 1. RHS will be what? 1 into 1 plus 1 by 2. This is equal to 1. Therefore, this relation is true for It's true for n equal to 1. You can check for n equal to 2 or you don't check. Initial value we got. Only one initial value you need to check. For n equal to 1 it is checked. So this was our basic step or basic step, whatever. This is the basic step we have done. Now we'll go for inductive step. What is that? In inductive step, we'll assume that let it be true for n equal to k. I mean this relation, let it be true for n equal to k. Let it be true for n equal to k. That is 1, 2, 3 up to k equal to k into k plus 1 by 2. Isn't it? This you understand? This k into k plus 1 that divided by 2. We assume that it is true for n equal to k. Now, for n equal to k plus 1, left hand side will be what? 1, 2, 3. K plus 1. Okay. For n equal to k plus 1, left hand side one more term will be added. But then what you are going to prove? Required to prove it is true for n equal to k plus 1 also. 1, 2, 3, k plus 1 going to be k plus 1 into k plus 2 by 3. LHS is like this. How to reach this one? This is principle of mathematical induction, no? True for n equal to k we have assumed. For that we are going to prove this thing. It is true for k plus 1. So let us start with this thing, that for n equal to k plus 1 what is happening? Till this, what we have assumed? Till this you have assumed that it is k into k plus 1. Told you. By assuming true for n equal to k, it will be true for k plus 1 also. So till this, we have k into k plus 1 by 2 plus k plus 1. Clear? So this thing will be see, it is proved. N into, sorry. So it is proved that it is true for n equal to k plus 1 also. So by proving it is true for n equal to k, we have proved that it is true for n equal to k plus 1. But we have already proved that what does the induction concept arise? K to k plus 1 true. Now what does the induction concept arise? But we have already proved that it is already proved that the relation is true for n equal to 1. So how does this inductive step helps? It tells you that if it is true for k, it will be true for k plus. So this implies that it is true for n equal to 1 plus 1, 2. Then how to get next one? Because you have proved that if true for n equal to k, it will be true for k plus 1 also. Okay. So this implies it is true for n equal to 2 plus 1, that is 3, and so on. Okay. So now write your comment that it is true for all positive integral values of n. Giving you one homework, just write it and try to get it at home. Prove by PMI Prove by PMI 1 square, 2 square, 3 square. Sum of the squares of first n natural number in n plus 1 to n plus 1 by 6. Okay, just try it at home. Similarly, for cube of sum of the cubes, 1 cube, 2 cube, 3 cube, so it is n into n plus 1 by 2 whole square. This you need to. Okay, you must try. Done. Now let us go for solving a few sums like we are going to apply now the principle of mathematical induction in solving sums. Kind of sums we have done in the last session, those also can be done with the help of mathematical induction. It's a very powerful tool. It's easy to apply, but don't ignore it. This will help you to verify your answer in some difficult problem. This will tell you to start a sum if by observation, if you have found that it is correct. Got it? So let us see how mathematical induction can be used to prove that 4 to the power n minus 1 is divisible by 3. Please don't use number theory. I mean, those formats theorem, congruency here. Just do by using PMI today. Okay? PMI means what? Principle of mathematical induction. 4 to the power n minus 1 is divisible by 3. We are going to prove it. So you take the expression xtn. For n equal to 1, T1 is what? 4 minus 1. This is equal to 3. So T1 divisible by 3. T1 is divisible by 3. Now there will be inductive step. Let us assume that let Tk equal to 4 to the power k minus 1 be divisible by 3. You first assume that. Then required to prove what? Tk plus 1, that is 4 to the power k plus 1 minus 1 is divisible by 3. Clear? Let us prove it. We have assumed this thing first. Tk equal to 4 to the power k minus 1 is divisible by 3. Now required to prove this thing. So now Tk plus 1 is 4 to the power k plus 1 minus 1. Isn't it? But this thing we can write this form. How to? You write 4 into 4 to the power k This you can write 4 into 4 to the power k, write minus 1 also. Write minus 1 also. Why? Because I need to get it in terms of tk. Tk divisible by 4 to the power k minus 1. This you write plus 3. So this is what? 4 into tk plus 3. What is our assumption? That tk, I mean this part, is divisible by 3. What about this part? Divisible by 3. So what about the sum? Tk plus 1, that is also divisible. It is proved by induction. Very first also. Many other ways are there that we'll come to know one by one. So how does it ensure that it is true for all natural number? Inductive step is done. For n equal to 1, it's true that we have checked. And now by assuming k, it is true for n equal to k, we have proved that true for k plus 1. This is induction. If true for 1, then it will be true for 1 plus 1, 2. If it is true for 2, it will be true for 2 plus 1, 3, and so on. So it will be true for all natural numbers. So long you are not putting any restriction on it. Okay. Now let us prove this one. 2 to the power 3n minus 1 is divisible by 7. How to prove it? You just think it first, then I'll first think. 2 to the power 3n minus 1 is divisible by 7. You just do 1 or 2 steps, then I'll start. Okay? Just do 1 or 2 steps, then I'll start. That is for n equal to 1 you do, then I do. Done. You write the same manner. Let Tn equal to, now T1 is what? Two to the power 3 into 1 minus 1. What do you get? 8 minus 1, 7. So you got the basic step. Base step, initial step. Therefore, T1 is divisible by 7. Clear? We have proved that T1 divisible by 7. Now let us assume that let it be true for n equal to, let Tk 2 to the power 3k minus 1 be divisible by 3. Therefore, Tk plus 1 will be what? 2 to the power 3 into k plus 1 minus 1. Okay? This you write 2 to the power 2k, 3k, 2q minus 1. You write 2q, I mean 8 as common. And there is minus 1 you have written, 2 cube into minus 1, minus 8. So you should write. Now what is your idea? That this thing, you have assumed that this thing divisible by 3. So here it lies. This thing, what? Divisible by 7. This is our assumption. We have proved for n equal to 1. This is divisible by 7. This part 7 is there. This is also divisible by 7. So what will be your conclusion? That if tk divisible by 7, tk plus 1 also divisible by 7. Hence the proof. Because we have proved that it is true for n equal to 1. I mean 3 1 divisible by 7. Now it will be 2 2 divisible by 3. 3 3 divisible by 3. Why? 3 3 divisible by 7. Why? Because inductive step we have proved that if it is true for k, n equal to k, it is true for k. That's clear. Understand? Let us go for next one. N cube minus 7n plus 3 is divisible by 3. One similar problem. I need not discuss. Hope you can try at home. Just copy the sum. I move to the next problem. I hope you'll be able to do it. Okay? Try. N cube minus 7n plus 3. You try at home. Take this one at home. Similar problem you must try. Let us go for next one. This is very interesting. This has many proof by using number theory, theorems, congruency, all these things. But today we learn it so that we can apply in future in any number theoretic problem. Can you follow me? Can you follow me? This we are doing just to apply in solving other problems in number theory. Proof can be given. Proof can be given here we'll do it by induction. Let us answer. You take the same manner, let Tn equal to x to the power n minus y to the power n. So T1 will be what? X minus y. X minus y because x to the power 1 minus y to the power 1. This is what? Divisible by x minus, isn't it? What will be your inductive step? Let Tk be divisible by x minus y. Now Tk plus 1. Tk plus 1 is what? What is the value of Tk plus 1? Just put it there. Tk plus 1 is x to the power k plus 1, y to the power k plus 1. Isn't it? This thing you write in the form of Tk. Is it possible? Let's see. No, it is coming in the form of y into y to the power k. You cannot take x as common. So what you will do there, you write x into, forcefully you are writing this. Then write plus x into y to the power k minus y into y to the power k. What have you got there? Plus. So first expression tk, it is divisible by x minus y. Second one you see x minus y as a common you got. So our conclusion will be the whole expression is divisible by x. You agree or not? This thing will be divisible by x minus y by induction, by principle of mathematical induction. Okay. Now one sum I have taken which is actually probably solved in the previous class. N into n square plus 5 is divisible by 6 for each natural number. You have to prove this. How do you do it? N into n square plus 5 divisible by 6. How to prove? We have done it by Euclid's lemma. We have taken n equal to 6k plus 1 or 3k plus 1. That I told you depend on the situation. Demand of the sum, whatever given, it is based on that. But here, today we have to do it with the help of PMI, Principle of Mathematical Induction. How to? Because I have taken this sum just to tell you that sum can be done by any method. Okay, you have the freedom to understand how it is divisible by 6. Number theory is very rich concept is there. Induction also a part of it, mathematical induction. Why, that you will understand. Okay, so let us do it by induction. Let Tn equal to, what will be the initial step? What will be the basic step here? That basic step going to be for n equal to 1. 1 you find 1 into 1 square plus 5, that is 6, divisible by 6. Again you assume let tk, k into k square plus 5 be divisible by what? Let this thing be divisible by 6. For that we have to prove tk plus 1. What is that? Replace k by k plus 1. Okay, k plus 1, k square plus 2k plus 6. This we got. Tk plus 1. Am I correct? Check once. I am just replacing k by k plus 1. Now, how to prove that it is divisible by 6? There is a 6, of course. But have you proved that the remaining term divisible by 6? Then it is done. We just know that k into k square plus 5 divisible by 6. So let us try to get that. It is k into k square plus 2k plus 6 plus 1 into k square plus 2k plus 6. You write k into so it is k into k square plus 5 plus, take it out now, 2k square plus k square plus 2k this plus 3k square plus 3k plus 6. Is that clear? You all understand? We got it there. But still it is not proved. What term we have got? That extra term 3 into k square plus k plus 2. Isn't it? 3k is there, this plus 2. Out of these, see how I am proving it. It is tk. This thing is what? See, k into k plus 1 plus 2. Is it done? Can you see where is the proof? This k and k plus 1, they are consecutive integers. Their product divisible by 2. This part divisible by 2. This part divisible by 2. Therefore, tk plus 1 is also divisible by 2. Okay. So if tk divisible by 6, we have proved that tk plus 1 also divisible by 6. This all that n into n square plus 5 is divisible by 6. Today's class I have just showed you alternative way to prove all this. Later on, they will catch the hand of each other and then you will find some beautiful application in number. Okay. So today's class till this only. I'll share with you some worksheets, links in the description. There you will find the worksheets on number theory. Okay. See you again next episode. We are coming with prime number, more of prime number, more of fundamental theorem, and more of Euclid's algorithm. Okay, get ready for that. I'll notify when the next session will be. Thank you for staying with me till the end.